Okay, let's jump into those examples. Determine the limit. For each one of these, we'll begin by checking that it's indeterminate, and then we'll proceed as we need to. Notice the first three are pretty similar. E to the 3x over 2x plus 2. We'll do the same function. That's as x approaches infinity. We'll do the same thing as x approaches -1 from the right. And then we'll change it just slightly to an x squared and look at x going to infinity again. Then D, E, F, G, we look at some different cases. D is still a ratio. Notice that E, F, and G are not ratios. They're not an f of x over g of x. So we'll have to rewrite these so that they are ratios first, and then we can apply the rule. So some similarities between E and F, and then G. I mean, that's its whole other thing. Okay, let's jump in. We'll start with A. Determine the limit. Part A. The limit as x approaches infinity, e to the 3x over 2x plus 2. Okay, first thing we want to do is make sure that this is an indeterminate form. We talked about this at the very beginning, one of the first slides, but okay. So as the limit, as x approaches infinity, e, if x is getting bigger and bigger, then our numerator is going to infinity. As this x is getting bigger, the denominator is going to infinity. So yes, that is an indeterminate form. Check. Okay, here's what I'm going to do. I'm going to recopy the whole thing so we can see how this rule works. We can say the limit as x approaches infinity, it's the same limit, but now we're going to perform derivatives on the numerator and denominator separately. Also, one other thing I should mention here, when you use L'Hopital's rule, when you write the equal sign, this is really like the only time I see this sort of thing happen. We're going to write L'H above the equal sign. When we're done with this step, we'll kind of look back and make sense why that is, why we indicate that we're using the rule. We don't do that in any other operation, right? Okay, let's see here. So it's going to be this fraction. So I'm going to take the derivative of e to the 3x. Well, that's a chain rule, right? The 3x is inside the exponent of e, so that's e to the 3x times 3. And my denominator, 2x plus 2, that derivative is a 2. Again, I take that derivative and that derivative separately. Okay. So why is it, let's kind of pause here. Why is it that we write the L'H? Imagine if we didn't. We just wrote this. If somebody else was looking at our work and we didn't indicate that we use L'Hopital's rule, they might look from here to here and be like, what are they doing, right? They might not pick up that we're taking derivatives and that we're using this rule, especially if there's a lot of other work going on. So just so everybody knows what we're doing when they look back at our work, we write L'H, and then they know, oh, okay, they're using L'Hopital's rule. So there's a derivative and there's a derivative and they're equal. Got it. Let me clean up that numerator, kind of write it like this. That looks a little bit better. Okay. Now, after performing the rule, what happens if we attempt to plug in the infinity again? Well, this time we'll get an answer. We'll have infinity again for the numerator and just 2 for the denominator. But of course, infinity divided by 2 is infinity. There you go. It turns out in this case, if you think of the tug of war between numerator and denominator, the numerator won. E to the 3x is going to infinity, much faster than 2x plus 2. As the x values are getting bigger, these numerator values are getting larger much, much faster than the denominator values are. So the numerator wins out, and the answer is infinity. Okay, let's take a look at another one. How about part B? We're approaching -1 from the right, same function, e to the 3x over 2x plus 2. So first thing we got to do, check to make sure it's indeterminate. We've got a new limit here. So is this still indeterminate? And if it is, then we can go from there. Let's see. If we plug in -1 in for x, I notice that my denominator is going to be 0. So just go for it, plugging in -1. I'd have e to the -3 over 0. You know what? That's not an indeterminate form. The only indeterminate form with the 0 on the bottom is 0 over 0, but we don't have that. We've got a number over 0. So what's happening here? There's a vertical asymptote at x equals -1, and a vertical asymptote, we will have an answer for the one-sided limit. We need to use a table. It's not indeterminate. So we should not approach it with L'Hopital's rule. And in fact, if we tried to approach it with L'Hopital's rule, we'd get the wrong answer. So don't do it. L'Hopital's rule is only good when you're seeing who wins the tug of war. But if there's no war to begin with, then that's just a misapplication, and it's going to lead us in the wrong direction. Okay, so here with the table, we're approaching -1 from the right, so numbers slightly bigger. And we're really just seeing, does this go to infinity or -infinity because of that vertical asymptote, right? Numbers a little bit bigger than -1, so maybe like -0.9, -0.99, -0.999. Grab my calculator. Let's see, e to the 3 times -0.9 divided by 2 times -0.9 plus 2. Okay, I got 0.336028. Okay. E to the 3 times -0.99 divided by 2 times -0.99 plus 2. 2.565166 when I round to 6 places. And finally, e to the 3 times -0.999 divided by 2 times -0.999 plus 2, 24.968327. Well, it's going, it's not going all that fast, but it's starting to pick up speed, right? From 0.33 to 2.56 to 24.96. Looks like it's getting larger and larger. And so this answer is going to positive infinity just based on the table. Okay. But really the point here was it's not indeterminate, so we got to use one of our old methods. How about part C? Limit as x approaches infinity, e to the 3x, changing it just slightly. Back to the limit to infinity. But now let's make it an x squared, e to the 3x over 2x squared plus 2. Okay, first step, check if it's indeterminate. Yep, here it would be infinity over infinity, check. So I'm going to rewrite this, and now we can apply the rule. It's the same limit as x approaches infinity. And our derivatives, well, 3 e to the 3x, this time over 4x. Interesting. Okay. So applying L'Hopital's rule, got our derivatives. If we attempt to plug in infinity again, will we have an answer? Check out what happens. Because now there's still an x in the denominator, when we put in infinity this time, it still results in infinity over infinity. This is still indeterminate. Oh no, does that mean L'Hopital's rule didn't work here? We still don't know what the answer is even after using the rule? No, because check it out. It's almost like a new problem. We took the limit of something, we got an indeterminate. So apply L'Hopital's rule again. Let's do it a second time. Who says we can only apply L'Hopital's rule once? If we do it and it's still indeterminate, well, it's like a brand new question. And we can apply the rule a second time, maybe even a third time if need be, and so on. So, okay, so doing another L'Hopital. Let's take derivatives again. Derivative of the numerator, 3 e to the 3x. Well, all of this would repeat, and then we'd be multiplying by 3 again. That would be 9 e to the 3x. The derivative of the 4x is 4, and I think we'll be able to get it now after our second L'Hopital. Plug in infinity again, and we'll get infinity over 4. That's infinity. Okay. So in the end, that e to the 3x in the numerator still won out. It was still going to infinity faster than 2x squared plus 2, even though we're now squaring the x. And so it's going quite a bit faster than it was before, still not enough to catch up with that exponential for sure. That exponential is getting bigger really, really fast. Okay, I bet, let's go for part D here. Part D is kind of interesting. The limit as x approaches 2, x minus 2 over x squared plus x minus 6. First step, of course, is to see if this is indeterminate. Well, if we plug in 2, what's going to happen? 0 on the top. 2 squared is 4, plus 2 is 6, 6 minus 6, 0 over 0. You know what? This question looks a lot like the sort of limits that we did back in chapter 2. But okay, let's kind of see what happens here. We got an indeterminate. Let's apply the rule. Okay. L'Hopital, limit as x approaches 2. Taking derivatives, we get 1 over 2x plus 1. No problem. All looks good now. We can plug in and get our final answer. Plugging in the 2, 1/5. Okay, why is this interesting? It seemed like a really simple problem, much simpler than the ones we've just been doing as far as derivatives go. Yes, this is the sort of problem that we did have back in chapter 2. How did we do it back then? We would have factored. All right. How would that denominator factor? One of them is x minus 2 times x plus 3. Get us the plus x and the minus 6. So we would cancel out and end up with the limit as x approaches 2, 1 over x plus 3. Well, would that give us the same answer as the L'Hopital? Yep, we plug 2 in and we get 1/5. So for this question, either approach would work. It is an indeterminate. So we can apply L'Hopital's rule, or we could simplify by factoring we're going to get to the same answer either way. So all of those questions back in chapter 2, where we had 0 over 0, it might have been possible to use L'Hopital's rule to get those answers, but we had, obviously we had to build up to that. We didn't know how to take derivatives at that point. So we had to do it by factoring or conjugates or whatever it was. There you go. Okay, that was fun. Let's stop this video here. I'll see you guys for some more examples in the next one.